introduce Rafael Oliveira, who will be giving this talk today. So he's currently at University of Waterloo and has done some really good work in this analytical algorithms. So he'll be talking about operator tensor scaling and analysis. Yeah. Okay, Rafael.
Okay, thanks, KB, for the introduction. Thanks everyone for coming. And let me figure out if I still know how to use PowerPoint. There we go. Uh-oh. Sorry, there is a... okay, there we go. Now it's better. Okay. Yeah, hi everyone. So today, as KB requested, I'll be talking a little bit about non-commutative PIT and kind of giving a little bit of the history on how PIT tried to be solved, and then we ended up kind of solving the non-commutative version of it. And then we're going to talk about how operator scaling comes in, and then we're going to talk about this analysis. Okay, and I'll bridge between the talks, like the previous talks from Ramadas and also from Ankit. Okay, so that like we can really see some concrete examples of things that Ramadas talked about, and a generalization of what Ankit talked about in matrix scaling. Okay, so okay, so today we're going to have some brief motivation, and then we're going to talk about scaling problems. And today, just for simplicity, I will just talk about matrix scaling, operator scaling, and draw a parallel between both of them. Tensor scaling is just kind of, the notation gets a little bit heavier, so I may just kind of assign that as exercise and pass by just the setup on Zulip for everybody. And then we're going to talk about some algorithms, and then the analysis and how PIT comes into play. And then we're going to give a motivation and preludes to like Cole's talk, and Cole will get into a lot more into the geometry of these problems. Okay, which will be another example, like getting further, like more concrete examples of all what Ramadas said before. Okay, so all right, so okay, why should we care about scaling problems, right? So, well, scaling problems actually appear in several different areas, not only in our beloved GCT and algebraic complexity, right? So, for example, if you think about Forster's techniques for sign rank lower bounds, it's actually a very special case of operator scaling. Okay, when you have like rank 1, when you have vectors, right? So these are called frames. In terms of algorithms, we can obtain deterministic approximation to the permanent of non-negative matrices, as Ankit talked about, via matrix scaling and mixed volume. And this is the work of Gurvitz and Symbolic. And in coding theory, like scaling was used for lower bounds on LCCs over the reals. And in optimization, we have Brascob-Levy moment polytopes and so on. In operator theory, we have Paulson problem, which is a beautiful solution using operator scaling. And but today we're going to focus on the algebraic complexity part, which is the non-commutative PIT. Okay. So, and recently there's been many more applications. So like in invariant theory, statistics, economics, some of them old, some of them very new. So it's a really exciting area, my biased opinion. Okay, so let's review a little bit of what Ankit talked about, since we're just going to generalize that. So we had the matrix scaling, or also matrix balancing problem, right? And we had before that an n by n complex matrix A is doubly balanced if, let's say, the L2 norm of the rows and columns of A are equal. Okay, so, and Ankit talked about the L1 norm. So I'm just going to give examples in the L1 norm, because L2, the numbers just become harder, right? So for example, in this case, well, L1 and L2 doesn't matter, but let's just use L1, L2, right? So remember that we talked about, so this matrix is doubly balanced because if you sum the rows, each row sums to 3 and each column sums to 3, right? So, okay. And we say that a matrix B is a scaling of A if there is these complex numbers like x1 up to xn and y1 up to yn, such that the product of the xi's and the product of the yj's are equal to 1, So if you think of the matrix, as Ankit mentioned, like the diagonal matrix with the xi's in the diagonal and the diagonal matrix with the yi's in the diagonal, we're talking about the special torus group, right? So this is the action of this product of two torus group on A, right? So what do? We just multiply, like xi multiplies the ith row and yj multiplies the jth column, right? So, and then we say that A has a doubly balanced scaling if there's a scaling B of A such that B itself is doubly balanced, right? So here's an example, right? So if I gave you this matrix in the bottom, which is 2, 1, 4, and half, and I did this scaling here, so this is x1, oops, so this is x1, this is x2, this is y1, this is y2, right? We get exactly the doubly balanced matrix above, right? So which would say that this matrix here, A, has a doubly balanced scaling, and we would call this doubly balanced scaling B. Okay. All right. So now, but Ankit, as Ankit mentioned as well, what we had was that, there's a difference between orbit and orbit closure, right? Of the problem of orbit and orbit closure. So sometimes we don't really get matrices which are doubly balanced, but we can get as arbitrarily close to doubly balanced. But what do we mean by arbitrarily close? And then Ankit also defined this distance to doubly stochastic or doubly balanced, right? Which is what? Well, we take, if you have a matrix A, let's say that Ri is the sum of the rows, of the ith rows of the matrix. And since I'm talking about L2 norm here, Li would just be the norm of the ith row. Okay, so you can always replace the L1 by L2. I'm just going to say norm, and you can put whatever norm you're comfortable with, right? So Ri is like the norm of the ith row, and Cj is the norm of the jth column. And here we're just normalizing by the total norm, just by saying, well, if you notice, if I normalize by the entire norm of the matrix, all we're saying is that if Ri over the norm of the matrix A, right? If they're all equal, then this ratio has to be 1/n. Right? So a doubly balanced matrix will be a matrix such that this dB of A is equal to 0. Right? Because literally, this is literally the distance from your matrix from being doubly balanced. Right? And we'll see how that comes up later into the geometric invariant theory that Ramadas talked about. Right? Okay. And then Ankit also defined that A has an approximate doubly balanced scaling if for any epsilon bigger than 0, right? There is a scaling B epsilon of A such that the distance of B epsilon to being doubly balanced is less than epsilon, right? So which means that in the limit, we will have a doubly balanced matrix, right? So this is equivalent to saying, in the orbit closure, you're going to have a doubly balanced matrix, right? Okay, so now, and the question that Ankit raised is, well, when does A have an approximate doubly balanced scaling, and can we find it efficiently, right? And Ankit also showed the connection to invariant theory, right? Okay, so here's some examples again, and the examples that Ankit gave you guys, so that just so that we can recap this and have this in mind, because they're going to come up in a little bit later, right? So if you remember, if I give you this matrix 1, 1, 1, 2, right, we have actually scalings to doubly balanced, and these scalings, well, even though our matrix is integral, it turns out that our scalings will not be even rational, right? So in this case, in a sense, algorithmically, you can also see why, you should care about orbit closure more so than just the orbit problem, right? The orbit problem is important in other settings, and especially if the groups are, if they're discrete, right? In which case orbits or orbit closures are the same, and then we have graph isomorphism and lots of other cool problems. But when the group is continuous, we should care about the orbit closures, right? So here's an example where algorithmically, okay, it would be impossible to try to find it if we use some optimization kind of setting to find exactly this matrix. But the other example that Ankit showed, which is more interesting from the geometric point of view, is this example, right? That if I have the 1, 1, 0, 1 matrix, then what happens here? then if I do this scaling, right, where here again, you have x1, x2, y1, and y2, right? Once you multiply those, what we get is that 1 epsilon square 0, 1. So we get really, really close to doubly balanced, but we can never get to doubly balanced, right? So, but this is in the orbit closure, right? Where we know the identities in the orbit closure. Okay. So, all right. So then Ankit, posed the problem of the matrix scaling. And remember, the matrix scaling was about L1 norms, but we need to talk about L2 norms. Talked about, right, where geometric invariant theory, we have a vector space and we have a group acting on the vector space, and we want to minimize the norm square and so on, right? So here we have a complex matrix A and a parameter epsilon. And the question that we want is there an epsilon scaling to doubly balanced, right? And if yes, we want to find it. So, and as Ankit showed, and there's an algorithm that was known to Kruithof, when he was working on telephone engineering, apparently, in the 30s. And it's much more known as the Sinkhorn algorithm, even though even Sinkhorn admitted that was already known for a while. So this is just the first documented appearances with Kruithof. Here, the algorithm is you repeat k times, right? Which is what Ankit described to you guys. We normalize the rows of A, and then we normalize the columns of A. Right, and normalizing is just make the norm of the rows equal and the norm of the columns equal, whatever norm you decide to choose, right? So, and then if at any point the distance to doubly balanced is less than epsilon, we just output the scaling that we have so far. Otherwise, we output that there's no scaling, right? All right, but then the thing is, well, and Ankit answered, I think, most of these questions, right? We're just going to discuss 3 that he didn't discuss that much, which was, so the question here is, are we making progress at all with this algorithm, right? And how do we know when to stop, right? And the third question is, well, is there some epsilon 0 such that if we can scale to epsilon 0, so if we can scale to epsilon 0 close to doubly balanced, then we know that we can scale for any epsilon, right? Is there a threshold? Because, if we want to say, if you give me an arbitrary large epsilon, it may be that, okay, it's really hard to try to optimize this and get to that close to epsilon. But if there's a particular epsilon naught that we know that, oh, if we can scale below epsilon naught, if we can get closer in doubly balanced to epsilon naught, then for any epsilon, we know we can scale. So we don't need to scale all the way there. We already know, right? So, and this third question has some importance, and we'll enter some non-commutative duality later. Okay, so all right, and again, let's just look at the examples that Ankit gave so that we can see what happens in this algorithm, right, when we actually scale. So okay, and I'm going to give the same examples that Ankit gave just for consistency, right? So we have this 0, 1, 1, 1, 0, 0, 1, 0, 0 matrix, and if I scale, well, let's normalize the okay. So here I am normalizing. The rows, and then I normalize the columns, and then I normalize rows. And doing this, you will see that this matrix somehow is tending. The more I normalize, this matrix is tending to 0. Okay, so this is the first example. Right, and if you remember, this was an example that Ankit mentioned. Oh, you cannot scale to close to doubly balanced, right? And somehow this example, the matrix is going to 0. Now, if you remember another example from Ankit's lecture, or just similar to the example that Ankit gave, it's just now we have 1, 1, 1, 1, 1, 0, 1, 0, 0, right? And remember, from what Ankit mentioned, if you draw the adjacency, the graph corresponding to this adjacency matrix, we have a matching. We have a perfect matching, correct? So in this case, okay, what happens when we scale? Well, so, okay, and now here I'm doing L1 norm just because L2 is just much harder, right, to do. So here we normalize the rows, and then we normalize the columns, and then we normalize the rows again, and normalize the columns. And as you can see, as this will progress, we're going to get to something that's very close to doubly balanced. Okay, so if you just do the scaling, we're going to get to very close to doubly balanced. And then, well, the question was how we can distinguish between these two cases, and Ankit discussed a lot about it. I'm not going to go much into detail. But the observation that Ankit gave was that in the first example, we have this huge block of zeros, right? Which is this Hall blocker, right? And the question was, are these the only bad cases? And Ankit proved to you, right, using the matrix scaling algorithm, that these are indeed the only bad cases, right? And again, the answer that Ankit gave was, well, it's yes, we can approximately scale to doubly balanced if and only if the bipartite graph has a perfect matching, right? And as we're going to see later in the lecture today, this is also related to like the Hilbert-Mumford criteria, right? So, all right. All right, so then why did I just give a review of Ankit's talk, right? Since we're already like well aware of it, is because in a sense, there's this connection between scaling and perfect matchings, right? So we want to find perfect matchings in bipartite graphs, right? But this is a problem that's very important, and it was very studied. It has been studied for a long, long time. You know, since before computer science, people already studying, right? Jacobi was studying this. So, so the thing is, okay, so the problem is, given a bipartite graph, does it have a perfect matching, right? And Edmonds had this following approach. Well, you know what? Like, given a graph G, let's just construct a symbolic adjacency matrix XG from our input graph, right? So let's say that our graph G is just this graph here. I have 1, 2, 3, 4, 5. Well, let's see, 1, 2, 3 here as well. So 1, 2, 3, and then let's say we have 1 goes to 2, 1 goes to 3, 2 goes to 1, 2 goes to 2, and we have 3 goes to 1, let's say, right? So if we look at this matrix, this is exactly the matrix that we had before, right? So the adjacency matrix of G is exactly 1, 1, 1, 1, 1, 0, 1, 0, 0, correct? So now what Edmonds said is, instead of constructing this adjacency matrix, let's just construct a symbolic adjacency matrix where, you know, whenever I had a 1, I'm going to put a fresh variable. Okay, so this fresh variable will be x11, x12, x13, x21, x22, and then 0. If I had 0, I remain with the 0, right? And then here I have x31, 0, 0. And what Edmonds said is that, oh, okay, you know what, like this graph, and if we look at the determinant, right, which we all know and love, and also we got exposed to that twin from Avi's lecture, if you remember from the determinant, what is the expression of the determinant? Is the sum over all the permutations. And remember, permutations here, they correspond to perfect matchings, right? So a permutation is a perfect matching the bipartite graph. And we just have the sign of the permutation, which I just write like this. And then I equals to 1 up to n, xi, sigma I, right? But now we know that each permutation corresponds to a perfect matching, right? In the complete graph, right? So if this determinant is non-zero as a polynomial, it must have been that I have a perfect matching in my graph. Does that make sense? So that's the reduction that we all know and love. So this was, you know, done by Edmonds, and actually Tutt did before Edmonds, actually, for the, you know, for any graph, right? We have the Tutt matrix, which is a little bit more complex. So this history is kind of a bit weird because they were both in Waterloo as well. So it's but those things happen, right? And as we'll see, it happened again, also for us, right? So, okay. And, you know, and then Edmonds in his paper, he just asked, you know what, like, so instead of just having this problem, so this, of course, that we know that if this happens, right, since this happens, like testing whether a determinant is different from 0, we know that we can do this in randomized polynomial time, right? We just plug in random values, right? And this is attributed to Lovász, right? Just plug in random values and it will be different from 0, right? So, okay. But then Edmonds asked this question, okay, given a linear symbolic matrix X, instead of just being the matrix with the fresh variable in each entry. Edmonds asks just a little bit more general question, which given a linear symbolic matrix, is the determinant of this matrix non-zero? Can we test this? Right? And as we know, via Valiant's work, we know that this is actually equivalent to the full PIT question. Right? So we know that if we want to generalize just the Edmonds approach from perfect matchings to, now the matrix X will be like just sum of AI xi, right? That I equals to 1, let's say up to m. We have m variables and the matrices are n by n. This is exactly the PIT, right? Via Valiant's work. Okay, so, and now, comes our hero, comes Gurvitz, and he says, all right, you know what? Like, can we solve PIT via optimization? Suppose that the only thing I gave you was gradient descent, Can you do something? Can you solve PIT? Right? And then let's delve into this approach on how to try to solve PIT via optimization, right? Because it seems kind of an algebraic question, but why not, right? So here's Gurvitz's approach to PIT, right? So what is our input? Our input here, and PIT here, may also be known as, SDIT, right? Which is like symbolic determinant identity testing. So if you come across these names, they're the same, right? So, all right. So given a symbolic matrix X, right, is the determinant of this matrix equal to 0 as a polynomial, right? So that's our question. That's the PIT question. It's a pretty hard question. But, Gurvitz is like, YOLO, let's try to solve it using optimization. Okay, so what was his approach? Well, his approach is the following. Let's construct this tuple of matrices A1 up to AM, right, from X. So suppose I'm giving it like white box, right? Like even solving white box PIT is a dream for all of us. So suppose that we know this matrix is AI. And what we're going to do is we're just going to construct this tuple A1 up to AM. And now, if you notice, if we act on A by simultaneously left and right multiplication by invertible matrices, by matrices determinant 1, does not change the determinant of X, right? Because let's say that L and R, they are two matrices. So these are in SLN square, right? So each of them is an invertible matrix with determinant 1. So now if I multiply, like if I make LAR to be equal, okay, I'm going to denote this as LA1R, LA2R, up to LAMR. Well, what is the determinant of this matrix? So let's say that X here, right? So if X is equal to AIXI, let's call this like XA of the tuple A. Now, the determinant of X, LAR, is equal to what? Is equal to the determinant of L times the sum of AIXI times R. Correct? But we know the determinant is multiplicative. So this is the determinant of L times the determinant of R times the determinant of XA. Right? So in particular, but we know that these matrices are in SLN. So in particular, this is exactly equal to the determinant of XA. Now, somehow, what did we arrive to? We arrived to a problem where we have a group, and this is our group. Well, let me switch slides because we have a group acting on a vector space. So what is the group? Well, our group will be SLN square is our group, and the vector space V is the vector space of matrices. Well, n by n matrices, but we have m of them. Correct? So we have this action of this group in this vector space. So let me say G is our group here. Okay, and now the idea is, well, let's look at this null cone problem for this group, right? So what is the null cone? Well, we have this tuple of matrices A, and the question is, can we send A to 0, right, by these group actions? So if we can, like if there are matrices like left that I multiply on the left and the right that take this tuple to 0, well, the determinant of XA will be exactly 0 because I can send all the matrices at the same time to 0. Does that make sense? So in particular, we know that, okay, if I have these matrices that I can drive the element to 0, right? So the idea here is that if I can drive the tuple A to 0, we know that the determinant of AXA must have to have been singular, right? And the question we should be asking, well, is this an equivalence? Right, so I'm going to save this question for a little bit, and it'll be much more clear once we dive into the invariant theory of it. Okay, and then Gurvitz asked this question, could it be the case that the null cone of this action actually captures the whole of PIT? Right, and and Gurvitz actually proved that in some cases the answer is yes. And if you want to look at his paper, like the class of matrices of spaces of tuples that he talked about, he termed them Edmonds-Rado, okay? Edmonds-Rado tuples. Okay, so if you want to see the terminology that he gave. But these are, exactly some of the cases that he actually proved that this is the same. Okay? And like if you want to see in other papers or in more recent versions of it, right? These are what we call like compression spaces. Okay. And compression spaces appear everywhere. Like they appear, well, in non-commutative algebra. They also appear in algebraic geometry, and many other places, right? So, and then they appear with multiple names, so which means that, okay, there's something cool about that, and we're going to kind of understand that in a little bit, right? So he was really motivated because now I was like, oh, okay, like I have some cases I can prove that this is just the PIT question. So, okay, now the only thing is, can we actually solve this null cone problem, right? All right. So, and then, Gurvitz is a quantum guy, so then he said, okay, let's just use this. Let's try to give this quantum approach to this question, right? So, and it turns out that, there are these quantum operators, okay? And quantum operators are maps that they map, let's say, in this case, the most simple setting, where we map n by n matrices to n by n complex matrices, okay? And it's exactly given by these tuples, A1 up to AM, okay? And these are called like the Krauss operators in this language, but, we can just think of them as this tuple that we have, such that, T maps a matrix X into this matrix, like sum of AIX, AI conjugate transpose. Okay, and the upshot of these maps, and why they're quantum is that they take PSD matrices, right, which are, kind of the generalization of probability distributions for the quantum setting, right, to PSD matrices. Okay, so this is the cool property of this map. And this map also has a dual. And this dual is with respect to, the Hilbert-Schmidt norm here, which is like the, your inner product is like X, A, B transpose, right? So if you look at this norm, you have this dual of this map, which is also very beautiful and it's very simple. It's just given by this T star of X, which is, you just flip the conjugate transpose, right? So it's AI conjugate transpose, X, AI. Okay. So, okay. And Gurvitz used these operators to give a generalization of matrix scaling. Okay, and hence will come the name of operator scaling, because it's scaling for these quantum operators, right? And now, Gurvitz was asking, what is the analog of scaling here? And what is the analog of doubly balanced? So what Gurvitz, and then again, remember his motivation, well, one of his motivations, he had many motivations to study this, okay? Quantum operators are also objects that are very natural in quantum information theory. So of course, there's lots of motivations from there as well, right? So, and the one that we want is just, can we solve PIT via scaling, right? By this operator scaling. So then he went on to define like the operator balancing problem, right? And then now we need to like generalize the matrix scaling problem. So the idea here is that a quantum operator, okay, is doubly balanced now if we say that the operator T, when you apply it to I, is equal to the T star of I, which is proportional to the identity, right? Which is the same thing that we talked about in the matrix setting, that all the rows and the columns are the same. And if you want to see how this generalizes, okay, So if you put the matrices AI, so here's an exercise. Let me just leave an exercise here right away. It's always good to do. So if we have like the matrices AI, let's say that the matrices are going to be AIJ. So we're going to have like n squared of these matrices, and they're going to be like square root of AIJ times EIJ, which is the matrix that has a 1 in the entry EIJ and zeros everywhere. Okay, so if we have these matrices as a cross operators, then operator scaling becomes matrix scaling. Okay, so that's just an exercise that you should keep in mind. This is really a generalization. Okay, and you can see that this conditional doubly balanced, it is exactly the condition that the rows and the columns, they have the same norm. Okay, so it's just as an exercise. All right, so now the scaling of Tx, okay, let me just, this is a little bit. Okay, I don't know how to, okay, should have done this on Beamer, but okay. All right, so now the scaling of T of X, it corresponds to, let me just rewrite here since I kind of, the scaling of T of X, it consists of two matrices. Remember the left and right matrices, right? Such that I multiply, like, remember, A will go to LAR, right? And that's the scaling of your operator, which is really, if we talk about invariant theory, we're talking about exactly this group acting on the vector space, right? So we're going to send the matrix A1, AI to the matrix LAIR, right? Simultaneously. And that's why this is also referred to as the left-right action, right? Because we're multiplying the matrices in the left and right at the same time. Okay, so, all right. So now, okay. And then Gurvitz also generalized the distance to doubly balanced because, well, if the condition to being doubly balanced is that, you know, Ti and T star of I, it's equal, like all the row, all this, these two operators are, you know, multiples of the identity, it better be the case that the distance to doubly balanced is exactly just the distance as a vector from our matrix Ti and the identity and T star of I to the identity, right? And here, what is the L2 distance as a vector is the Frobenius norm of these matrices, right? So that's why we have Frobenius norm here. It's just because we're saying, well, okay, there is this vector T sub I that we have, right? And we just want as a distance as a vector to like the identity essentially, right? And these factors like the norm squared and 1 over n is just the normalization that we need. Okay, so this is the distance from you being doubly balanced, which generalizes the distance that we talked about for a matrix being doubly balanced. Okay, and okay, and again, just as an analogy, we know that Tx has an approximately doubly balanced scaling if for every epsilon bigger than 0, there is a scaling, L epsilon and R epsilon, such that this operator that's given again, if you look at this, this is exactly the image of the group action, right? And we know that this operator has this distance to doubly balanced less than or equal to epsilon, right? So you can see how it's line by line a generalization of matrix scaling, right? But now we have a non-commutative group action, right? Because Ankit talked about tori, and now we have non-commutative groups, right? Okay, excellent. And then the questions are the same, right? So, you know, when does A1 up to AN have approximately doubly balanced scaling? And can we find it efficiently? And the third question, right, which, you know, what does this have to do with invariant theory? And you may be asking, well, but you're told me already this is a group acting on a vector space. Indeed, I told you that. But in a sense, this doubly balanced scaling, what is the relation of this scaling to doubly balanced that is related to invariant theory? What does this correspond to the general theory that Ramadas talked about, right? And we're going to see a little bit today that this is exactly this non-commutative duality paradigm. Okay, so like it fits very much, everything here fits very much into the geometric invariant theory, which of course it was not clear to any of us until very recently. So okay, so I'm hoping that after this will be clear to everybody, right? So all right, so then here's our problem, right? We have this operator T, which again we can just give by these matrices A1 up to AM, right? And then we have this epsilon bigger than 0. And the question is, can T be epsilon scaled to double stochastic, right? And if yes, we want to find the scale. Okay, so Gurvitz did, okay, well, that algorithm that we know for matrix scaling works just fine. So why not just do the same algorithm for the operator scaling, right? It's generalized in such a beautiful way that you can just plug in everything the right way. So what do? We're going to repeat this k times, right? We just left normalized T of X. And notice that if I multiply the matrices AI on the left, I can actually make T sub I to be proportional to the identity. Okay, but then of course, I'm going to mess up the dual, the T star of I. And now what do? I need to fix T star of I. And then now I just need to write normalize. By write normalize, I need to multiply the matrices AI by some matrix on the right. And if I do that, I can make the dual to be whatever I want, right? Like to be close to the identity, to be the identity. And if at any point we have that the distance to doubly balanced is less than epsilon, we just output our scaling, right? Otherwise, we output that there's no scaling. Okay, so then the questions are the same that we had for matrix scaling, right? That Ankit answers is, well, which case should we choose here? For how long should we run this algorithm? As the first question. And again, we had that third question that was still not addressed that we're going to talk a little bit about today, which is there an epsilon naught such that if I can scale to epsilon naught, then I can scale for any epsilon, right? Because if I have this epsilon naught, then I can actually solve the null cone problem, right? And I'm going to tell you why we can solve the null cone problem as well later, right? This is still not clear as well, why this epsilon naught is so important to solve the null cone problem, and how is this kind of related, right? Because right now we have not talked about the null cone problem. We're just talking about scaling to doubly balanced. Somehow these are not yet connected, right? So, okay. So here's the analysis, right? And again, we're just going to use the LSW type analysis because everything just follows so beautifully, right? Such a beautiful generalization. And the steps are what? We are going to find an upper bound. We're going to find a potential function, okay? And the potential function here is quite clear. It's the same as we kind of talked about for the matrix scaling. We're going to use the potential function. Here is the norm of the input. And here, I'm going to do things a little bit different from Ankit, right? So I'm just going to use the potential function as the norm of your input. So here, for the matrix, in the matrix scaling, we would just use the norm of the matrix. And for the operator scaling, we're just going to use the norm of the tuple of matrices, okay? And clearly, this potential function phi has an upper bound because it's upper bounded by the input size, right? So, okay. And now we're going to do exactly the same step as Ankit did, right? Which is what? We're going to show that every step, we're going to be making progress. So if we're really far from doubly balanced, then what we're going to show is that normalization, this normalization that we're doing will decrease the value of the norm by a multiplicative factor of, exponential to O of epsilon. It's the same thing that Ankit did, right? So I'm not going to do that calculation here. Okay. And then the third one is a lower bound. Okay. What do? Well, we start with a measure that has an upper bound, and we say, okay, if we're far, so long as we're far from doubly balanced, this norm will keep decreasing. So you can see now how we're going to the null cone problem because we're using the norm as our potential function. And we're saying, if we're far from doubly balanced, our norm will keep decreasing. So if I keep being far from doubly balanced, my norm will go to 0. It has to go to 0, right? So, all right. So this is, you can already start seeing that there's a connection between this and the null cone because of our potential function. And then we have a lower bound that if there is a scaling to doubly balanced, then there's some property that should tell us that actually the norm is bounded away from 0. Right? So somehow you already see here that there is some property, okay, that's telling us that, oh, if I can scale to doubly balanced, then it must be the case that I'm not in the null cone. Because what is the potential function? Our potential function is that the norm is our potential function. And we're saying that the norm is bounded away from 0 if I can scale to doubly balanced, right? So somehow this is capturing the null cone. And we just need to figure out what this property is, right? Okay, so now, if you notice, this approach will prove correctness and running time of, polynomial in n, b, and b is the, the bit complexity, like the size of your input over epsilon, right? And this is the same analysis as Ankit gave, exactly the same. So I'm not going to do these calculations just to give the conceptual message, right? But if you want it as an exercise, you can do this. All right. So these are the 3 steps, and these are the 3 steps that we'll apply. We just need to figure out, okay, what is the sum property here? Okay. And all right, so let's talk about the matrix scaling again, and let's just revisit that analysis, right? So what are the 3 steps? Our potential function now, which would be a bit different from Ankit's, is that we're going to use the norm of the matrix squared, right? And is upper bound by the input size. And if you just do the same thing as Ankit did by using the norm, you can see that if we're epsilon far from doubly balanced, then this normalization will decrease the value exactly by this multiplicative factor. Okay. And the lower bound here was, well, if you remember, if A was not in the null cone, there is a nice invariant polynomial P, such that, if A is not in the null cone, this piece of A is different from 0, right? So, and as Ankit mentioned, well, one of these invariant is the permanent, right? Which was nice, but there's an even nicer, like, invariant, which are the matching monomials, right? And these are like the permutation, right? If you just take a permutation, there's one permutation. If you're not in the null cone, you have a perfect matching. So look at that perfect matching that corresponds to a permutation, and you take the monomial corresponding to the permutation, right? I'm going to do this like explicitly here, right? And the idea is what? The idea is that, this invariant, and this is where invariant theory is coming in, right? So if this polynomial P is invariant, P sub A is equal to P sub B for any B in the orbit of A, right? And also in the orbit closure, right? By continuity. So I'm going to put also a bar here. Correct? Okay. And now, well, the idea is, what is this niceness about this invariant is that, well, if P is a polynomial with integer coefficients and our matrix A is an integer input, we know that, okay, P of A is different from 0 means that the, absolute value of P of A is an integer, right? So P of A is an integer. And if it's an integer, we know that this absolute value of this integer is greater or equal to 1. But what does it mean, the absolute value of this integer being greater or equal to 1? It means that the norm of B is greater or equal than, inverse exponential in n. Right? And inverse exponential is okay because, remember, we're always decreasing by a multiplicative factor, which is also an exponent, right? It's e to the minus epsilon, right? So we're always multiplying by e to the minus n. So this e to the minus n is totally fine, right? So, okay, so we know that, and this is for any B in the orbit closure of A, which means that if A is not in the null cone and A has integer entries, right? So that's important, right? Like if A is not in the null cone and integral, then we know that its orbit closure, okay, is far away from 0. So we have this gap, right? So, all right. So again, this proves correctness and running time, as Ankit showed. So, all right, what are the invariants that we could take for matrix scaling, right? So if you remember from Ankit's lecture, is just we have the double torus is acting on a matrix, and now the matching monomials are the invariants. So what are the invariants? Ankit showed, right? Like, so if I had this monomial here, like, B I sigma I, remember each monomial, each matching corresponds to a permutation, right? That we talked about. This is a permutation. So if B is equal to XAY, Ankit showed in this lecture that this monomial, right, which is the product of BI sigma I, and sigma here is a permutation, right? So this corresponds to a perfect matching in our bipartite graph. right? Then this is equal to the product of AI sigma I, right? Just because we can extract this product of xi, yi. Okay, so this is the same calculation, right? And, as Ankit talked about, the Birkhoff von Neumann theorem, right? Like this invariance turns out to generate all the other invariants. And this is also something really nice, because if you have a generating set of invariants, right? Well, we know then that if A is not in the null cone, right, by Hilbert's theorem, then we know that P of A is different from 0 for some matching. So there is a matching such that this matching will witness that A is not in the null cone. And as we saw in the algorithm before, instead of using the permanent, we can just use any invariant, right? Any such invariant. So then what happens here? Again, if A has integer coefficients and, P of A is different from 0, then we know that PA squared is greater or equal to 1. And again, B is in the orbit closure of A implies that the norm of this P, because P is an invariant, it doesn't change at all, right? The norm of PB is greater or equal to 1. And again, in this case, if we use that, if we use that PB is a matching monomial, it was a product of integer things, right? So it will still remain an integer. So we know that P of B is actually an integer. So we can even get a better bound than what we had before when we use the permanent, because the permanent we're kind of giving a very loose bound. And here we have just that the norm of B to the 2 to the n is greater or equal than the norm of the evaluation of PB, which is greater or equal to 1, right? So we have even a better distance if we look at the invariants more carefully instead of just using the permanent, right? But using the permanent is important because that algorithm gives an approximation to the permanent, which is very interesting, right? So there's these 2 points of view that you can talk about, right? If my goal is to give an approximation to the permanent, I better use the permanent. But if I'm just talking about the null cone, I can use a better invariant. Okay, so, but this is not, it's not super essential, right? Your running time just gets a little bit worse, but all right. And again, what was the analysis of the algorithm S, right? Well, okay, the analysis was, again, which is, analogous to the LSW, which Ankit showed, right? So we look at the norm of our input, and the norm has this bound. Well, the L2 norm, like the Frobenius norm of A, is just, upper bounded by nu square, and nu here is the maximum absolute value of an entry, right? Times n squared. So this is the bound of the input. And, LSW showed that if your distance to doubly balanced is bigger than epsilon, then the norm will decrease by this factor. And if you remember, this was the first example that I showed you, right? I just showed that example, how the matrix is going to 0, right? So, but the thing is, if you notice, if your matrix was integral to begin with, and you have a perfect matching, right? What we just showed in the previous slide is that the norm of any scaling of A will be greater or equal to 1. Right? So if my norm was, nu square n squared, and I had a scaling, I cannot decrease this much multiplicatively if I must be lower bounded by 1, correct? So if I just run this long enough, right, which is just like nu square, well, log nu square n squared over epsilon times, right? Either I must have that I'll be very close to doubly balanced, or my norm will drop below 1. But if my norm dropped below 1, I know I cannot be scaled. I know I'm in the null cone, right? Because I know that no invariant could have been 1. Does that make sense? So somehow this matrix scaling is actually showing us, well, okay, so if we get a norm low enough, it's also a proof that all the invariants are 0, which means they're in the null cone. Does that make sense?
Yeah.
So in this case, what we just showed is that if the matrix is integral and there's a scaling that drops the norm below 1, this matrix is in the null cone, right? So this algorithm here is answering the null cone question. And similarly, yes. Okay. So, and similarly, now let's do sorry. Oh, sorry. Okay. So let's do now sorry, I pressed too many buttons. So now let's do the analogous to the operator scaling here. Okay. So let's just do the same analysis, but let's look at operator scaling. And now remember, if for matrix scaling, as Ankit mentioned, and as we just reviewed, like the main idea was that, oh, the invariants are the nice properties, right? So we need to look at the invariants for operator scaling. Now, what are the invariants for operator scaling? The invariants for operator scaling are what? Well, okay, let's look at some invariants. We certainly know from Gurvid's intuition that, okay, the determinant of my matrix X is an invariant, right? So if I had that tuple, remember, if my tuple X, XA was sum of AI, XI, we knew already that the determinant of XA is an invariant. Correct? But the thing is, you know, this is not the only invariant. Because look, notice that suppose that instead of having XI was a variable now, but suppose that XI, they are 2x2 matrices. Right? And then like, well, okay, how do I multiply a matrix by another 2x2 matrix? Well, we tensor them, right? So suppose now that we have this like sum of AI tensor a 2x2 matrix YI. Now YI is a symbolic matrix, okay? So YI, like all the 4 entries are different commutative variables, right? So if I look at this example, what happens? Well, it turns out that the determinant of this quantity here is also an invariant. And why is that? Well, let's look at the computation. Let's say that this polynomial here, okay, is a polynomial like Py of A, is this polynomial. Now, let's say that B is a scaling of A. So we have that Bi is equal to L times A times AI times R. Now what happens? Let's look at Py of B. Py of B is the determinant of the sum of Bi tensor Yi. Right? But now Bi is equal to L AI R. But now notice that this is the same as just writing like, you know, L tensor the identity times determinant times sum of Bi tensor Yi times, and here's a matrix, the times are matrix multiplications, right? Like R tensor the identity, correct? So this expression here is exactly the same as this one.
Yeah.
Right? Because I can just pull out the left and the right multiplications. And now I have true matrix multiplications. But what happens, what is special about these two matrix multiplications? Well, this guy, again, the determinant when you just multiply is multiplicative. So then I have the determinant of A, sum of AI tensor Yi. Oh, sorry, this should be AI here. Okay. And now, well, what is the determinant of this matrix? Well, is the determinant of L to the power of the dimension of the identity. So let's say that Yi's are D by D matrices. So that I get determinant of L to the D times determinant of R to the D. But now remember, our group is the special linear group. So these determinants are 1. So these guys vanish. They're equal to 1. We can hide them. And this is exactly equal to the determinant of sum of AI tensor Yi, which is the Py of A. That makes sense? So this Py's, they are also invariants. Right? And now this should give you a hint. Oh man, like we're not getting PIT here because we're not testing only if the determinant of XA, which was the quantity we're after, is 0 or non-zero. It could be the case, right, that my determinant is 0, but there's another invariant, which is one of those that could be non-zero. Right? So, we're like, oh man, okay, this looks like it's not really PIT, right? Because now we have these other invariants that are intervening into our golden goal here. Okay, so now, all right, so let me just erase my mess here, because this is just to explain that they were invariants, and I don't want to mess up the other slides. I promise next. Hopefully the next talk we can use a better technology called Blackboard, right? So, all right. And then here, now note that, okay, as a result, it's a result of King, actually, okay, that they generate all the other invariants. Okay, these invariants that we talked about, these new invariants, when we replace the X size by like D by D matrices, if we just keep replacing them by bigger and bigger matrices, these invariants actually generate all the other invariants. So now we know that our tuple A is not in the null cone, okay, by Hilbert's theorem, if and only if, okay, Py of A is different from 0 for one of those invariants. It could be the determinant, but it could also not be the determinant, right? So there should be a hint that we're like, okay, we're not quite there yet. Okay, we still have our jobs, right? Like, the grad students still have future, we haven't been able to solve it, right? So, okay, but now, what can we use here, right? So suppose now that I look at these polynomials, like Py sub B. Now, Py, I just need to tell you which matrix is Y I'm using. So let's just say that I pick the Yi's to be matrices with integer coefficients, right? So I know that my tuple of matrices is a tuple of integer matrices. I know that the Yi's are integral. So then I know that Py of A, if Py of A is different from 0, then it's an integer, which means again that its norm is greater or equal to 1. Right? That's the nice property of the invariant. Now, and we know again by the same reasoning that if B is in the orbit closure, then we also know that the norm of this polynomial Py at B is equal to the norm Py at A, because it's an invariant. And it has to be greater or equal to 1. Now, these invariants are not as nice as the matching invariants, right? Like that, they're not super nice. But then, all we know is that this will be a degree n times d polynomial, right? Which has integer entries, right? So, okay, so this is a homogeneous polynomial, right? And now, what can we do? Well, okay, let's look at this polynomial PYB, and we can just upper bound it in the most obvious way, right? So just look at every monomial, okay? And we look at the coefficient of this monomial, and then we just upper bound like the monomial itself by the norm of the matrix B to the degree, right? So our degree here is 2nd, right? Because we have this square, and our polynomial had degree nd. And then how many monomials do we have? We have exactly exponential n times d monomials, right? And then we can just give this upper bound. Okay, so this is the upper bound that we have, okay, on the norm of the PYP. And now we know that this is greater or equal to 1, which means that if I'm not in the null cone, I know that the norm of my scaling will be greater than e to the minus n. Right, just by this reasoning, because I have to, I have a d here and I have a d here, but the d's get canceled out. Right, just because we have an exponential, but we also have a power of n to the d. Okay, so notice that this does not depend on the degree of the invariance, right, which is quite nice. All we need is one invariant, and then okay, like this invariant, this kind of degree kind of it vanishes. So we're saying again, like, what did we prove? That if I'm not in the null cone, then all my scalings will be far from 0, right? All right, so now let's just look at the analysis, and is analogous to the analysis that we did before, right? So if we have our normalization and the analysis here, which came like, 11 years after Gurvitz, right? So was what? Again, we just use the norm as our progress measure, as a potential function. And again, just by generalizing the LSW, we can say if the distance to W balance is bigger than epsilon, then this norm square would decrease by this exponential factor. Okay, but we also know that the norm of the vector of the tuple B has to be bigger than or equal to exponential minus n for any scaling of A, if A is not in the null cone. So again, if we run the algorithm by the same number of steps that we had before for matrix scaling, if our norm does not drop that much, then we know we will have, if A is not in the null cone, our norm cannot drop too much. So within that number of iterations, we will find an element that has a small distance to W balance. Right? And if A is in the null cone, right? Okay, I haven't talked about the epsilon yet. If A is in the null cone, it could also be that I can find an epsilon close to W balance for an element in the null cone, right? But if I don't, I know that after running a bunch of times, I know that my norm will drop below exponential. So now we need to talk about this epsilon. What is the epsilon that we need to set to talk about the null cone, right? Because given some epsilon, some things in the null cone can achieve that close to W balance, right? Like think about it. Trivially, if epsilon is infinity, then any norm is finitely close to W balance, right? Now we can say, oh, what if I have distance 1 to W balance? It could be that things in the null cone can be 1 close to W balance, right? But so what is this epsilon that we need to set so that we actually can decide membership in the null cone, right? What is this distance to W balance? So, okay, so the question should be like, oh, okay, have we solved the null cone problem? The answer is like, well, I don't know yet, because I do need to figure out what the epsilon is, right? All right, so, okay, but now before we talk about this epsilon, okay, let's just talk about, have we solved PIT? And, you should already be thinking, no, of course not, right? Otherwise, what would we be talking about here? We're just celebrating and partying, right? So, sure. Okay, the algorithm G solves the null cone problem for the left-right action. We're going to talk about that soon, right? But is this equivalent to PIT? And the answer is no. Okay, how can we see this? Okay, well, we can see this by looking at our, super cool example. Of this Q-symmetric matrix. Okay, so because all we need to show that this is not equivalent to PIT is something that has determinant 0, right? So it's singular, but this algorithm fails for it, right? So if we look at this, well, the determinant of this matrix is clearly 0 because this is an alternating matrix, right? A Q-symmetric matrix of odd size. So this determinant, the symbolic determinant is 0. But now, okay, so the determinant of this matrix is equal to 0. But if you plug in x to be equal to 0, 1, 1, 0, y to be 1, 0, 0, 0. Now notice that x and y don't commute, okay? And z is 1, 1, 0, 0. Then the determinant of that big matrix will not be 0. Okay, gives non-zero determinant. So we have an invariant, which is not the determinant, for which it does not vanish. So our algorithm will be like, okay, this matrix, if we were trying to solve PIT, the algorithm would be wrong right here. It would say, oh, okay, this matrix here is not is not singular. But as a matter of fact, we know it's singular. Does that make sense? So, and it's quite interesting because coming up with more examples like these is quite it's quite nice. I mean, of course, we know that alternating matrices will be such an example, right? But like finding more examples is also an interesting question, right? Like to figure out, oh, we have more examples like this. And the answer is like, yes, we do have some. There's some constructions by Drysma and so on. So this is quite nice. Okay, so we know that it's not equivalent to PIT. Then it's like, okay, what is this null con good for then? You know, like, sure, you're solving null con, you talk about fancy words, but what is this good for? Now, I'm a complexity theorist. Does it solve any problem we care about? The answer is like, yes. Okay, so due to the works of Kohn in the 70s and 80s, and also Hilbert and Mumford, we can see that actually this non-commutative rational identity testing. So now suppose that you have, you know, we want to do polynomial identity testing, but instead of using commutative variables, you use non-commutative variables. Because if you remember, the invariants that we had before, they were like determinants of, instead of just plugging in xi's to be commutative, if I plugged in non-commutative values, which are matrices, we got all the invariants. So this must be something non-commutative. And funny enough, actually, I should put another name here, right? That Amitsur already knew this, kind of. But then with the works of Kohn, it became really clear that this problem is exactly the same. So Amitsur in the 50s, okay, he showed that if I have a rational expression, which is kind of like, think of the rational functions when you don't commute, right? So he showed that like a rational expression, non-commutative expression, is equivalent to 0 if and only if these determinants, well, the determinant when we evaluate this non-commutative expression, let me say phi, the determinant of phi, when you evaluate at some matrices y, this will be 0 for all y, for all dimensions. Okay, so that was already back in the 50s. But then Kohn, what did he do? Kohn actually did, in the non-commutative world, okay, what Valiant did for the non-commutative world, for the commutative world. And Kohn did it before Valiant. Just kind of cool, right? So like this result was kind of like already there. We just didn't know about it, right? And so Kohn just showed that any non-commutative rational expression can be encoded by a tuple of matrices exactly in a similar way that Valiant did, but now we don't have a determinant of non-commutative stuff. So what is this rational expression? So if I have a rational expression phi, what Kohn did is if this phi has size s, and guess what? Kohn said that this can be equivalent to the sum of ai xi, I equals to 1 up to m, inverse 1, 1. The 1, 1 entry of the matrix inverse. And here is inverse on the free skew field, okay, like the non-commutative version of the field. And this is of size, these matrices have size s. If this sounds awfully familiar to you, is because it should, right? Like is exactly the, you know, the non-commutative analog of saying that matrix inverse is complete, is a complete model for formulas. Okay, it's a beautiful result, right? So Kohn in the 70s already did this. Okay, and okay, so and this, he did this non-commutative version, and okay, and he also proved that a non-commutative rational expression evaluates to 0 if and only if this a1 up to an or am, sorry, they have a shrunk subspace V. Now, what is a shrunk subspace V, right? So a shrunk subspace V, okay, is just a space that all of the matrices AI, when you multiply them by the vector space V, this gives you another subspace, right? And this subspace, let's say, is contained in a space U, where the dimension of U, all of them, okay, this is for all I, where the dimension of U is less than the dimension of V. Right? It's just saying that all these matrices simultaneously, they will shrink this space V. They will send V to like a space of smaller dimension. Right? So, okay. And okay, and then, okay, if you look at this shrunk subspace, and then if you look at Hilbert-Mumford's theorem, and you also look at the one parameter subgroup, you can see that this shrunk subspace is equivalent to this tuple being the null con. Okay, so, okay, let me see if I have time. How much time do I have? 0 minutes?
10 more minutes. 10 more minutes.
Oh, 10, okay. So then if I have time, let me keep going through the conceptual part, but otherwise I'll show you how you can also use this to show exactly the same of this one. You can really see that the shrunk subspace gives you the one parameter subgroup. Okay, so I'll do that if we have time later, or you can ask me a question in the question period. Happy to answer that one, right? So, all right. So now let's just recap this foundational results, right? And now let's put together all the invariant theory and Ramada's talk together with this result, right? So, okay. So given a vector space and a group acting on it, right, we know that this null cone is the zero set of all like the set of all elements such that zero is in the orbit closure, right? And we know that, okay, an element is in the null cone if and only if all the invariants vanish on this set, right? So this is something we learned. And the null cone problem was, given this V in our vector space is actually V in the null cone, right? So this is our null cone problem. So just a recap of the previous lectures. And now we saw, right, with Ankit's talk and my talk, right, to begin with, there's two ways of solving this problem, right? One is the algebraic one that comes from the definition. Well, do all the invariants vanish, right? So for that, we need to find a generating set of the invariants or a separating set or a null cone set. Those are different sets, but right. So and we want to decide if all the invariants would vanish. So that was one PIT version, but the other version is an optimization version. Is that, well, we have the optimization version of the definition, which is what Hilbert already talked about, is zero in the orbit closure. So all we do is we need to solve this problem here. Like, can we minimize this norm? And is this norm zero? If it's zero, we know. If the infimum is zero, we know we're in the null cone. If it's not, we're not in the null cone, right? So, okay. And okay, and now, okay, so why are we talking about this? Where is doubly balanced coming from, right? Because, you know, somehow that there's something about the norm. We could see that algorithm is decreasing the norm all the time if the, you know, if the doubly balanced norm is big. So, and now here we come to like Ramada's talks, right? And we just see that actually, okay, if we look at the null cone problem, right? If we look at this optimization viewpoint, right? Ramada's also talked about it, right? So there's this Kempf-Ness connection that says, well, okay, how do we know that we're close to this optimum of this program, right? Of the minimization of the norm. Well, okay, Kempf-Ness, they showed that, okay, we're close. Well, we know from, you know, convex, right? Like we have our convex and non-convex optimization that, okay, close to the optimum means that our gradient has to be close to zero, right? And the gradient here is the gradient as Ramadas defined, which is the gradient along the group action, which is related to what Ramadas was talking about, the moment maps, right? Because the moment maps were the gradients along the group action, right? And okay, and then there's a general notion of convexity here, which, you know, Kempf-Ness proved, and Cole will be talking a lot more about in his lectures, right? So, but now let's just see what happens from Kempf-Ness when we apply to operator scaling and matrix scaling, right? So if you remember from Ramada's talks, right? So we have that the moment map is this gradient along the group action, right? And therefore, we can create this dual program, okay? Because now we can say the dual program, we have the capacity, which is the minimization of the norm. But now we have the dual program, which is, let's minimize actually the norm of the gradient. So here, we're minimize norm of the gradient, right? So this is a different problem. And what Kempf-Ness proved is that actually these problems are dual. In which sense? They showed that, you know, the capacity is equal to zero. What does it mean the capacity is equal to zero? We are in the null cone, like the norm, the infimum of this norm is zero, if and only if the gradient is always positive. Does that make sense? So that's the result of Kempf-Ness. That's the seminal result, one of the seminal results of Kempf-Ness, right? And essentially, what is this doubly balanced? So now we get to the bottom of it, why does this doubly balanced problem kind of solves our null cone? Is because doubly balanced, when you compute this doubly balanced of A, doubly balanced of T, they're actually the norms of the moment map. So the scaling problem that I just showed to you is not this one, but it's this one. Right? Because notice this norm of the moment map is our gradient. And all that we're doing, if you remember, the norm of the moment map is exactly the distance to doubly balanced. So all we're doing is that, okay, let's try to minimize the norm of doubly balanced. Right? And if the minimum is bigger than some value 0, is always bigger than 0, and is a bit far from 0, we know that we must be in the null cone. Okay? So Kempf-Ness are just telling us that if you're far from doubly balanced, essentially, it means that we're in the null cone. Okay? And okay, if you want to ask another question, another great question is, well, how do we compute the moment map to see if it is the doubly balanced, right? I could do that in a little bit, and is a good exercise to also put it kind of in concrete terms, all the, kind of general picture that Amadas actually gave us, right? So I can do that later if I have time. And then we need to talk about the lower bound for the moment map and the null cone, because now, remember, we have that question, which epsilon should we choose? And as it turns out, right, you can actually prove that for matrix scaling, okay, we can actually prove, which is proved in LSW, that if you choose epsilon to be bigger than, I think, let me just be safe here, like 1 over n squared, I think 1 over n should be okay. Like, sorry, less than or equal to 1 over n squared is good enough. Okay, so we have the separation. And for operator scaling, Gurvitz showed that the same epsilon suffices. Same. And you might wonder, wow, is this such a coincidence? And it's great that the epsilon is polynomial, because remember, our algorithm runs in time polynomial of 1 over epsilon. So it's really great that these epsilons are actually 1 over n. Otherwise, we're really doomed with those algorithms. Right? And you may wonder, wow, okay, like matrix scaling operator, they have the same, we proved that they have the same epsilon. And is this a coincidence? And the answer is no, if you look at our more recent 100-page paper that does a lot of this tour, that it has to do with exactly kind of the commutative part of the representation theory of these groups. Okay, so it has to do with these weight margins, which they actually come from the commutative part of these groups. Okay, so this is not a coincidence, but it turns out that the lower bound here is that for any epsilon, so maybe I can put this epsilon naught here, right? Like that epsilon naught that we were talking about. So you can take this epsilon naught to be 1 over n squared, and then you can decide whether we are in the null cone or not. Okay. So, all right. And now let's just summarize what we learned today, right? So we have our operator T, which is given by this tuple of matrices, and the question of the null cone problem, or actually the moment map minimization, right, in Ramadas kind of language, is what? Can T be epsilon scale to double stochastic? And if so, we want to find the scaling. Well, again, we just do the same algorithm that we did for matrix scaling, right? And now we already know which K we should choose by the potential function analysis, right? And we used K to be the norm. And again, is there an epsilon naught such that if we can scale to epsilon naught, we can scale for any epsilon? And remember, this epsilon naught would decide null cone via the Kempf-Ness theorem, right? And we notice that here, okay, take epsilon naught, let's say equals to 1 over n squared, and it should be okay. So then we did solve the null cone in polynomial time in this case. And we saw also that the null cone in polynomial time is exactly equivalent to the non-commutative PIT for rational expressions, right? So, okay. And now just another comment before my time is up is that, this algorithm is also really a primal dual approach of optimization. right? Because if you remember, what are the primal and dual programs by Kempf-Ness? The primal programs were minimizing the norm. The dual programs were minimizing the norm of the moment map, which is the gradient. Now, by Kempf-Ness, those problems are dual to each other. And what are we doing? If you look at this algorithm, it's doing exactly that. Because here, what is this doubly balanced? The distance to doubly balanced is being big, is that we're far from the dual. We're trying to minimize, and we say, okay, if we're epsilon, we're far from, let's say, if the minimum was 0, right? Like, we're far from the dual, which means that we make progress in the primal, right? And in a sense, we also know, like, the normalization, it's one thing that we forgot to tell you, is that the normalization is doing, so this normalization can be seen as actually a gradient descent. So when you look at it from an optimization perspective, actually this is a gradient descent. But because we're doing this alternation, we don't start with the full gradient, we do block gradient descent. Okay, block coordinate gradient descent. Okay, and I'm just saying this because this is a prelude to Cole's talk, where you're going to see this optimization language a lot better, and it'll be a lot clearer. And I mean, Cole is a lot better than me, so then, you know, you'd be even better. So when he gives the talk, right? So, and the same thing here for the algorithm G. Okay, so the same thing, we have the same template, and again, as we saw, like, this distance to doubly balanced is the norm of the moment map, which is the dual problem. And if we're far from the dual, we make progress in the prime. Okay, so, okay, and now, if we're really just interested, not in the PIT, you're like, no, you know, you guys convinced me these talks were amazing in the GCT program. I just want to work on invariant theory. Now I want to solve the orbit closure intersection problem. I don't care. Let's try to solve it. Okay. So if you remember, what is the orbit closure intersection problem? Well, if you give me any point, you take its orbit closure. And now if we take 2 points, we want to know if the orbit closures intersect. Right? Now, if one of the points is 0, then it becomes the null cone problem. So the orbit closure intersection is a generalization of the orbit closure problem. Right? And we know the null cone is very important. So you're like, oh, the orbit closure intersection must be even more important. So let's solve that one. Right? Now, well, how can we solve the orbit intersection problem for the left-right action, for example? Right? So orbit closure intersection, right? So what do we need to do? Well, it turns out that operator balancing that we saw now, the operator scaling, is not enough. Okay? And why is it not enough? Is because orbit closures, actually, they can be exponentially close and not intersect. Unlike the null cone. If you have 0 and you're an integer point, you will be far, as we saw. You'll be very far from 0. But you can have 2 integer points that they themselves, the orbit closures, will be exponentially close. So our epsilon that we have now for orbit closure intersection, the epsilon naught, is exponential, is inverse exponential. And our algorithm runs in time 1 over epsilon. So, okay, so with that's not going to work. So what do we need? Well, we need to have this epsilon to be, you know, exponential, like e to the minus n, let's say. So then we're kind of doomed with our current algorithm. And this was not the case for the null cone problem. As you saw, we can take epsilon to be 1 over n squared, for example. And again, operator balancing runs in times poly n over epsilon. So this is only good for the null cone. So we need an algorithm that gives us log 1 over epsilon convergence. Then we go polynomial again. But for that, we need a different algorithm, right? And this different algorithm, to get this algorithm, we actually need to explore a little bit more the geometry of this Riemannian space that we're at. And this is something that Cole will do with the geodesic convexity. And, you know, so, okay. And this is just a prelude to Cole's talks, and I'll end here.
Wonderful. Very nice. And a good advertisement for Cole's talks also. Lovely. Yeah. So are there any questions for Rafael? You got 3 claps. Very nice talk. Yeah. Yeah. I think these talks have sort of connected up really well, I think. Yeah. Yeah. I think this is very clear talk. So I don't think there are questions. I don't know. Any questions? Nobody's raised hands. Okay, so maybe one thing that you sort of said, or will you put it up on Zulip?
Yeah, I can put some exercises there for people to discuss and maybe also
nice, I think.
or send to someone so that just to practice, right? Because I feel like even for me, I feel that this language sometimes it's so general and so kind of that sometimes I like to see a simple example where I can just, oh, what is the moment map? What is the how to compute those things, right? So that they become familiar to us in the settings that we are applying.
Correct. Yeah, so Ramdas's notes also mentions this moment map. He didn't talk about it in his talks, but it is there in his notes actually. He actually calculates it in some examples. But I don't know whether it connects up to what you will do in your exercises, but it'll be nice to have that actually.
Right, yeah, because I mean, in Ramada's talk, like he talked about the Hamiltonian and then also like the moment map, right? Like, so if like in the lecture 3, right? Like, so he was talking about that. Oh, okay, like there's the Hamiltonian and there's also like the gradient in the Riemannian space, right? That those two like are the same and they correspond to the moment map. And it's actually funny because this correspondence is kind of how we compute the moment map. So if I go back to the slide to, you know, just kind of answer a question that I'm going to ask myself. Oops. Right. So here, how do we compute the moment map for this action? Right. So let's say that our function here, I'm just going to use the function. You know, I have my matrix A, my current matrix is my tuple of matrices A, and I have my left and right, which is the group action. Right. So we can just say that this function will be like the log of the norm squared. Okay. So I'm just going to do like log of the norm squared of LAR, the norm squared. Right. So how do we compute like the gradient with respect to the group action? Right. And the way to do it is actually kind of not to go directly, but to use this correspondence of the moment map that Ramadas talked about and to say, okay, the gradient of this function at the identity, right? Like FA at the identity. If I take the inner product and the inner product now from the Riemannian geometry that we get, right? Like and the inner product here is the Hilbert-Schmidt like inner product anyways, like is the sum of the two. So if I take this with the inner product of the infinitesimal direction, and what is the infinitesimal direction? Well, here, well, L, if you look at the exponential map that he talked about as well, right, the Ramadas talk, L will be e to the like h, maybe let me see, e to the, yeah, let's say e to the h1, and then R is e to the h2, right? Where this h1 and h2, they're the elements of the Lie algebra of our group, right? So then this would be like the inner product between this and the direction, h1 and h2, because remember, the Lie algebra gives us the direction, right? So this is, we're going in direction, like given by h1 and h2. These are the elements of your tangent space, right? So if I do this, so by definition, this is the gradient, right? The gradient inner product with your current direction gives you the directional derivative. But what is the directional derivative? We can see the directional derivative exactly by doing it through the exponential map. So this is the derivative with respect to t of our function fa when I go in that direction. But how do I go in that direction? Well, e to the t h1, e to the t h2. And then I evaluate this as t equals to 0. Correct? So this is our this is how we compute the gradient, because now, well, H1 and H2 are just like kind of symbolic directions, right? You can think of H1 and H2 as symbolic directions. And then, you know, I can just compute this, and I take the derivative and I evaluate this to 0. Now, this is a problem that is just univariate calculus, right? That we can just do, which is, let me write it like this. I really like Michael's notation for this. So the derivative of t, and then we evaluate t equals to 0 of this function, like log e to the t h1, like the norm, a e to the t h2 norm squared, right? And then this is exactly like, if I take the derivative, I take 1 over the norm of, and this norm is exactly,
squared.
right, let me just do
value.
e to the t h1, a e to the t h2 norm squared, right, is 1 over, like, then like log of x is 1 over x times, and I use the chain rule. Now I have to take the derivative of this guy in the middle. Now, what is the guy inside? If we just write this guy inside, it will be the derivative of t, right? Like, and it will be equal to, what is this guy inside? It's exactly the sum of I equals to 1 up to m of the norm of the Frobenius norm now of ETH1 AI ETH2 Frobenius norm squared, and I evaluate everything at t equals to 0. Now, if you compute this, what you end up is exactly with your formula that, so I'll leave that as an exercise and we can put it on Zulip, right? And then if you compute that, you end up with this following formula that your gradient, let me just put it like this, our gradient of f of a, and the identity is going to be this vector, right? Like this 2 vectors. So it's going to be 1 over the norm of a squared, 1 over the norm of a squared times, and then if you just do the computation without noticing one thing, you're going to get t of I, t dual of I. Yeah. But then you may look, well, okay, but this does not look like the distance is doubly balanced, right? We're missing that minus the identity. So what is going on here? Well, what's going on is because we didn't tell you where this guy lives. But if you remember from Ramada's talks, this gradient has to live in the dual of the Lie algebra, which we can identify with the Lie algebra. So this guy is in SLN cross SLN. But these are like the traceless matrices. And all we forgot to do here is to subtract the trace part, right? So once you subtract the trace part, so subtracting the trace, we actually get a identity. We actually get, and you're going to see that this TI has trace exactly 1 over norm of a squared, right? So then what we get is exactly like 1 over norm of a squared TI. When you subtract the trace, you have to subtract something of trace 1, which is exactly the identity, right? Like, because orthonormal means that this vector here has to be orthogonal to the identity, right? So this is orthogonal to the vector identity. So then we subtract, like, and then we have 1 over norm of a squared, t squared of I minus 1 over n identity. So yeah, so I can put these as exercises on Zulip. It's great to compute for matrix scaling, to compute for operator scaling again, and it's the same strategy. Is this strategy here that we usually compute?
Any more questions? Let's thank Rafael. Thanks, Rafael. Lovely talk.
Thank you. Thank you for the program. Yeah.
Thanks.